I'm spaceflight historian Amy Shira Teitel, and let me tell you, the upcoming total solar eclipse on August 21st is definitely a once-in-a-lifetime event not to be missed. And if you can't get anywhere to see it in person, why not tune in to Time's live stream coverage? We're going to be talking to people in the field in the path of totality and sharing their views. It's going to be an incredible event hosted by yours truly. And not only are eclipses just beautiful, cool things to see, they're also scientifically very important. In fact, almost throughout most of human history, scientists have been using eclipses to study space and really understand the universe that we live in. Eclipses happen all the time. Technically speaking, an eclipse is just when one body in space is obscured by another body crossing in front of it. So they happen all the time, but what's rare is being in the right place at the right time to see it. Like a solar eclipse, the moon passes between the sun and the earth every month. That's what we see as a new moon. But it's rare that the three bodies actually line up so perfectly such that the moon obscures the sun from any given point on earth. Ancient civilizations knew this. They studied the sky the way some of us study our favorite TV programs, and that included eclipses. The earliest recorded sighting of a solar eclipse was by pre-Socratic philosopher Thales of Miletus. He predicted a total solar eclipse would happen sometime during the year 585 BCE, and he was right. It happened on May 28th of that year. Modern astronomers have worked backwards to confirm that yes, a total eclipse did happen where Thales would have seen it on that date. No one is entirely sure how Thales was able to predict that eclipse, but it's possible he had an understanding of two solar cycles that let him understand that it would be happening that year, the Saros cycle and the Exeligmos cycle. Another solar eclipse was seen by Plutarch on March 20th of the year 71. He wrote of the event that even when the moon covers the sun entirely, a kind of light is visible around the rim, which keeps the shadow from being profound and absolute. It's possible that his observations were the first time anyone in recorded history actually saw the solar corona. So ancient astronomers studied eclipses and they knew what was happening. They understood that it was the moon blocking the light of the sun. They had also studied the phases of the moon to understand that the Earth and the moon were both spherical, not flat. And interestingly, all of this still worked within the geocentric universe, the Aristotelian cosmos that had the Earth at the center with all of the planets orbiting around it. When we're talking about eclipses, it's easy to explain it whether the Earth is orbiting the sun or whether the sun is orbiting the Earth. It helped, too, that eclipses happen at relatively regular intervals. This all fit within Aristotle's model of the cosmos, wherein everything is perfect and unchanging. Of course, all of that fell apart with Copernicus in 1543, when he published in De Rev that the sun is actually the center of the solar system, not the Earth. In addition to decentering the Earth from our understanding of the cosmos, Copernicus was also a fan of eclipses. Copernicus used a pinhole camera to observe 4 partial eclipses in 1530, 1536, 1540, and 1541. Tycho Brahe also studied eclipses to try and measure the moon's diameter, as did his apprentice Johannes Kepler. Of course, using pinhole cameras, and even with Kepler's revelation that orbits are actually elliptical and not perfectly circular, their measurements of the moon's diameter were an estimation at best. Eclipse observations got more interesting in the 19th century when astronomers started using telescopes, not unlike those that Galileo Galilei used to discover the moons of Jupiter. They also started using secondary instruments like prisms to study the sun during an eclipse. French astronomer Jules Janssen traveled to India to view a solar eclipse on August 18th of 1868. Using a telescope and a prism, he noticed there was a bright yellow spectral line from right around the sun's corona. The discovery was independently duplicated on October 20th of that year by English astronomer Norman Lockyer. Together with English chemist Edward Frankland, they named the element Helios after the Greek word for the sun. Studying a solar eclipse is how we discovered the element helium. A little more than a decade later, during the 1879 eclipse, another pair of astronomers independently discovered what they thought was a new element called coronium. But it turned out this wasn't a new element at all, but rather exceptionally hot iron in the solar corona. It was studying a solar eclipse that astronomers learned that the sun's corona is unbelievably hot, millions of degrees hotter than the sun's surface. But perhaps the most interesting thing we've learned about the universe from a solar eclipse is that Einstein was right with his theory of general relativity. Hundreds of years before Einstein, Isaac Newton published the Principia and laid out his view of the universe. It was a neat and orderly one governed by forces and laws. But Einstein's work on relativity in the early 1900s went against Newton in many ways. Namely, he argued that space is not static. For Newton, space was inert and unchanging. For Einstein, objects can change structures in space. Einstein used the fourth dimension of time to create what he called the fabric of space-time. Whereas Newton held that light traveled from, say, the sun to the earth by photons moving through the vacuum, Einstein said that they traveled on a straight line but could be warped along the fabric of space-time by the gravity of a larger body. It's almost as if space-time is a trampoline surface and a planet is a bowling ball. A photon is a marble rolling along it, and while it might bend its path around the bowling ball, to the photon, it's still traveling in a straight line. For Einstein, gravity was an effect of the warping of the fabric of space-time, whereas for Newton, it was a direct attraction. The problem for Einstein was he needed some way to prove it, and an eclipse was the answer. Sir Frank Watson Dyson, the Astronomer Royal of Britain at the time, came up with a way to test Einstein's theory. He measured the position of stars that would be near the sun's limb during an eclipse, then measured their position again during an eclipse in 1919. He found that the stars' positions had changed. There was a pronounced warping by the sun's mass, destroying once and for all Newton's idea of inert space. And of course, this eclipse will be no different. While most people just go outside to look at something incredible, to see darkness in the middle of the day, scientists will be doing various experiments to try to learn a little bit more about the sun and our universe by studying this solar eclipse. Thank you guys so much for watching, and I hope this got you a little bit more excited about the upcoming eclipse. And speaking of, be sure to subscribe to Time's channel so you don't miss out on our live streaming event on August 21st. And if you are fascinated by spaceflight's history, specifically the Apollo era, be sure to check out my own channel, Vintage Space, where you will get weekly videos unpacking things you never thought to even ask questions about.